When building robots or any system that needs high torque, a gearbox is usually almost always needed. And amongst the 3 standard gearboxes being planetary, cycloidal and harmonic drives, there's always one that I think stands out, which is cycloidal drives. A cycloidal drive is a gearbox actuator that reduces the input speed in order to increase torque on the output transmission. This gearbox is known for its features with backdrivability, minimal backlash and in some cases zero backlash, minimal vibration and a pretty compact size. Cycloidal drives are really well suited for applications where backdrivability is useful and where you want as little backlash as possible, but they're also really well suited for basically anything, from robotics to machine tools. The fundamentals of a cycloidal drive are all based around the ring shaft, the actual cycloid and the roller shaft, and the eccentric cams. The cycloid might look like it's spinning like a normal gear, but what's actually happening is that as the eccentric cam input rotates, it pulls the cycloid along with it. But this also pushes the cycloid against a ring of rollers, the ring shaft. And because of the increased value of ring shaft rollers to cycloidal disc lobes, the cycloidal disc is forced to rotate in a weird eccentric cycloidal motion, which then results in driving the output pins, the roller shafts, in the opposite direction of the input at a reduced speed relevant to what the reduction ratio is. For the cycloid to complete a full lap of the ring shaft, the input shaft has to complete a full rotation multiplied by whatever the reduction ratio is. This little model cycloidal drive I have here has a 20:1 reduction ratio. So for this cycloid to complete a full rotation of the ring shaft, the input shaft has to rotate 20 times. I don't know if that was in focus. Wait, this fucking focus. In doing so, this creates the wiggly little weird motion that the cycloid makes. And with the use of the roller shaft, it can output the rotation of the cycloid into a linear rotating motion, which is something we can actually use. So taking apart my cycloidal drive design, there's a gorgeous diagram on the left and a CAD overview on the right, where inside the ring shaft there's the important moving parts, which you're going to have to imagine moving. Taking off the top part of the roller shaft, you can better see the implementation of the roller pins. Now without the roller shaft entirely, there's just the eccentric cams and the attached cycloids, which leaves us with just the cams and the raw dogged motor. In a standard cycloidal drive, the roller shaft works as the gearbox's output and the ring shaft works as a sort of body of the gearbox, as it's physically mounted to the motor's body. Although in some cases these principles are swapped around so that the roller shaft is mounted to the motor's body and the ring shaft plays as the output. The main difference between these two variations is that the one where the ring shaft is the output, it causes the output to be closer towards the middle of the actual gearbox, which just means more sensitive gravity, but it also has restricted motion, whereas the normal cycloidal drive has full 360 range of motion. Now addressing the motherfucking elephant in the room, which is the gear ratio of one of these motherfuckers. And it's really not that deep, it's just the amount of lobes that are on the cycloid. So for this, I have a 20:1 reduction ratio gearbox, which means that this cycloid has 20 lobes on it. But the ring shaft always has one more lobe than the cycloid. So this 20:1 reduction ratio gearbox has a ring shaft with 21 lobes. The actual shape of a cycloidal disc is based around the geometry and relations of trochoids, which is a curve traced by a point on a circle's circumference rolling along a line. There are heaps of variations of trochoids, but two of the main relevant ones are epicycloids and epitrochoids. An epicycloid is a curve traced by a point on a circle's circumference rolling along the circumference of another circle. The other variation of this is the epitrochoid. This is fundamentally the same as an epicycloid, but the point that's traced is a point that's offset from the center of the circle. An epitrochoid is actually what a cycloidal disc is based off of. The shape of a cycloid is actually pretty far from what a cycloidal disc actually looks like. It's more so just like a base shape of a normal trochoid. To form an epitrochoid, you need parametric equations like the one on screen. Although these equations alone can't complete a cycloidal disc, because if you wanted a cycloidal disc, you need to include parameters like the eccentricity, ring shaft lobes, and roller shaft rollers. Now obviously the torque output is mostly determined by the actual gear reduction, but there's still a pretty big factor that contributes to the torque output as well, and that's eccentricity. Technically eccentricity is all this and all that shit, but no one gives a fuck about all that. Eccentricity is just the offset of the cycloid and cams from the center of the gearbox. Actually I lied, no, it's not just it. The curvature of a cycloid is completely relevant with the offset of the cycloid from the center of the gearbox. And that curvature of the cycloid ties in with the entire gearbox's performance. For example, having a higher eccentricity will technically produce more torque, but because of the higher surface area contact of the higher curvature of the cycloid, it causes unreliability due to friction and just unbalance and just inefficiency. It's just shit. But having too low of an eccentricity can cause the gearbox to just lose torque altogether, and sometimes the gearbox just slips. So really, you gotta find the eccentricity sweet spot between effective and efficient. And the one I have here is usually a pretty good in between if it's gonna fucking focus. But as they say, a new year comes a new gearbox. So I thought I'd make the perfect gearbox for your middle class cunts. This is a 5-axis robot arm, and it's something I made about a year ago. Now, the thing about this robot arm is that each joint operates off of a cycloidal drive, and throughout has about 3 different attempts and iterations of a cycloidal drive, which I physically printed and tested out. Sketching cycloidal discs in CAD can be pretty tricky for your average fucking Joe. But in saying that, you want to try not fork the cycloid from any other people's open source projects. Mainly because the whole post-process of designing is way simpler if you know and chose all the actual parameters like eccentricity and offsets, but also so you feel less retarded. After some looking around, I found what looked to be the 2 best ways of properly designing a cycloidal disc in a CAD sketch. I thought I could either manually sketch out each point and angle following Levi Jansen's tutorial, or I could follow this paper on SolidWorks cycloidal drives. Even though it's meant to be made for SolidWorks and it's built an equation-driven curve function, I was really invested in this because I've tried the other way before, the more manual way, and it fucking sucks. It's the age of automation, we need to do better. Even though I'm stuck with Fusion 360, which for whatever reason doesn't have an equation-driven curve function, you can easily modify the equation, plug in your parameters, and insert it into this Fusion add-on, which I've heard is really useful. All I have to do is download it, and what the f***, it's been removed. After crying for a few days, I found out about this way to plot sort of equation-driven curves using Python with Fusion's custom API add-on system. Originally, I was trying to make my own Python API code, but trust me, that was not going f***ing anywhere. But eventually, I realized that someone had probably already done this, and big surprise, they had. To design a cycloidal gearbox, you have to download this GitHub file, extract it, and import it into your Fusion 360 scripts in this file directory. When you do this, make sure to drag the cycloidal drive file that's inside of the cycloidal drive file. Once you've done that, if it hasn't shown up in your Fusion 360 scripts, press the green little plus and select the cycloidal drive file. After you run it, now you can actually plug in your parameters and insert it into your sketch. The parameters on screen are the ones that I have. After you insert and extrude the cycloidal disc, you can start sketching out the roller shaft and the ring shaft for your cycloidal drive. By the way, the files for the actual proper finished design of my gearbox, as well as some useful sources and the code for the stepper motors, should be up on my GitHub. Now when scaling all of the moving parts, I've made sure to add just enough room for both clearance and tolerance for the 3D print. I'd say the sweet spot, at least for me, is to have about 2ish to 4ish mil of space in between the cycloid, the ring shaft, and the pins. With this gearbox, I'm running a 20:1 reduction ratio, which I think is a pretty fair and standard reduction ratio for cycloidal drives or any gearbox really running with a stepper motor. Before I go any further, we got to discuss budget. To utilize the maximum and best performance of a cycloidal drive, you need a lot of ball bearings in place of the ring shaft, lobes, and roller shaft pins. This eliminates a lot of performance issues, including friction, that naturally comes with the use of 3D printed parts. Although the issue in doing this is the price, as the cost of bearings can add up really fast. And if you're like me and not interested in spending that much money, you might want to consider just simply not using bearings where it's not necessary, like in the ring shaft rollers and the roller shaft pins. But keep in mind, this can cause up to 50% less efficiency. Because I'm not using bearings in the ring shaft or roller shaft, I can still use low friction materials like metal or nylon parts, instead of just simple 3D printed parts. For the roller shaft, I'm using 5mm outer diameter and 3mm inner diameter nylon rods that has an N3 screw running through the middle to secure the actual roller shaft in place. But something to keep in mind, and something that I've personally had to deal with, is that if the rods aren't perfectly squared, it'll completely fuck up the gearbox's performance due to the pins being slightly off axis. To start up the build, we're just going to be drifting all the bearing to the cams. And this one I've already done, because when I was testing the gearbox, obviously I put it all together. But I couldn't get the bearings off the actual cam, so I sucked my dick. Normally I do have to use the hammer to whack it in, but just because I've taken these out and put them back on so many times, it's loosened up a bit. These are 8mm thick and the bearings are 7mm thick. So these discs are 180 degrees out of phase, and I've got a little hole so I can just put a screw in temporarily and just keep it lined up. Now we can slide in this bad boy Okay. I think it's done nice and fair. Alright, so I think that's operating nice and smooth, so we'll chuck it in here. It would be way smoother if I added grease, but I'll be doing that later on off camera because it's just a really big pain in the ass. And this is the finished gearbox. Before I do anything else, I want to tighten up. I'll move all light for this. I want to tighten up the screw, keeping the shaft in place. There is one thing that could be considered a problem, is that the way that I've designed it and just the materials that have been used, you can see a bit of wiggle. And this is partially because of the clearance of the roller shaft, and it's also just because of the bending of the plastic, but that happens when you have a really 3D printed gearbox. Alright, so the little setup we got here, we've got the code running on the laptop, and that's running in through the Arduino Mega, which is then hooked up to this TB6600. That's hooked up into this, which is hooked up into my power supply, running off of focus, running off of 26 volts, 27 volts, whatever you want. That's enough yip yap. Let's put it front and center and see how it goes. What's up, bitches? So here is the magical gearbox, and it's unplugged at the moment completely, and this is just a shaft that back driving. It's not terrible, it's pretty good. That's 2 kilos. We're gonna lift it up. Please be the right way, I forgot. It's lifting that alright. 3 kilos, we'll run that and see what happens. All good. Okay, let's go. Yep, there you go, okay. It's gonna struggle. That is about to fucking snap and fall on my foot. 4 kilos, let's do it. Don't know what I was expecting. Alright, so we're running 3 kilos again. Easy shit. Alright, so that gave us about 10 Newton meters of torque, which is pretty fucking shit. Considering the motor that I'm using is rated at 2 Newton meters, this gearbox is a 20 to 1 reduction ratio, which means that it should technically be a max of 40 Newton meters. 10 Newton meters of torque, when it should be 40, which is 25% efficiency. So